In 1913, a scientist named Henry Moseley, he showed that atomic number is a more fundamental property of an element compared to atomic mass. So, he redefined the periodic law suggested by Mendeleev. We know what is Mendeleev's periodic law states. It states that properties of elements are the periodic functions of their atomic masses. Now, Moseley, what he did, he understood that atomic number is a more fundamental property than atomic mass of an element. So, he restated Mendeleev's periodic law as properties of elements are the periodic functions of their atomic number. This is known as the modern periodic law. When atomic number was considered as the basis of classifying elements in the periodic table, the defects that the Mendeleev periodic table had all could rectified when this atomic number is considered as the basis of classification. Now let us have a look at the modern periodic table. The modern periodic table has 18 vertical columns known as groups and 7 horizontal rows known as periods. In this chapter, we will discuss about the first 20 elements, that is from hydrogen to 20th element calcium. Now let us consider the first group elements of the periodic table. What are the elements in the first group? Hydrogen, lithium, sodium, potassium, etc. Let us consider the first 4 here. Now what is the atomic number of hydrogen? That is the first element. So its atomic number is 1. What do you mean by atomic number? It will have 1 proton, or you can say it will have 1 electron. Now the electronic configuration of hydrogen element is 1 and it can be depicted as shown close to the electronic configuration. So in the first shell of hydrogen, 1 electron is there. Let us consider the second element in the first group. Which is the second element? That is lithium. What is the atomic number? 3. So what will be its electronic configuration? That will be 2, 1. In the first shell, 2 electrons can be accommodated and the remaining 1 electron goes to the second shell. So it can be depicted as given here. Now let us consider the third element in the first group. So the third element is sodium. You see, what is the atomic number of sodium? That is 11. So what will be its electronic configuration? 2, 8, 1. In the first shell, 2 electrons. In the second shell, 8 electrons. And in the third shell, 1 electron. Now let us see the fourth element in the first group. That is potassium. What is the atomic number of potassium? 19. So what will be its electronic configuration? The first shell, 2 electrons. Second shell, 8 electrons. Third shell, 8 electrons. And fourth shell, 1 electron. So electronic configuration is 2, 8, 8, 1. Do you see anything particular when you wrote the electronic configuration of this first group elements? Yes, you see, what is the last number of electron? You know, in the outermost shell, what is the number of electrons? You see, it is 1. It is 1. So all those elements belongs to first group. So its outermost shell has 1 electron each. Now let us consider group 2. You see, what are the elements in group 2? First 2 elements of group 2. They are beryllium and magnesium. What is the atomic number of beryllium? That is 4. Now what is the electronic configuration? 4 can be written as 2, 2 because the first shell can accommodate maximum 2 electrons. So the remaining electron goes to the second shell. So electronic configuration of beryllium is 2, 2. What about the electronic configuration of magnesium? Its atomic number is 12. So 12 can be written as 2, 8, 2. That's the electronic configuration. Now can you tell me the number of valence electrons in the outermost shell of these elements? That is 2. Why? Because these elements belongs to second group. So in second group elements, all will have 2 electrons in the outermost shell. Now let us consider the 17th group elements. You see, 17th group elements, the first element is fluorine, the second element is chlorine. Let us consider those two elements. What is the atomic number of fluorine? 9. So what will be the electronic configuration? 2, 7. So what is the maximum number of electrons that can be accommodated in the outermost shell of this element? That is 7. Now let us look at chlorine. What is the atomic number of chlorine? That is 17. So it can be represented as 2, 8, 7. So outermost shell has also 7 electrons for chlorine atom. You see, in 17th group, so all elements will have 7 electrons in its outermost shell. So from this, what we conclude? We conclude that down the group, all elements will have the same number of valence electrons. First group elements will have 1 electron, second group elements will have 2 electron, and so on. That is the first we observe from this position of these elements. Now what can you say about the number of shells as we go down the group? See, the first group element let us consider. In the first group element, which element belongs to the first period? See, hydrogen belongs to the first period. So when the period is 1, how many shell that element has? It has 1 shell. Now let us come to the second period in the first group. The first group element belongs to the second period is lithium. You see, lithium belongs to second period. Now what are the number of shells? It has 2 shells. Let us look at the elements in the third period which belongs to the first group. You see, the third period element belongs to the first group is sodium. Sodium belongs to period number 3. So it will have 3 shells. Now what about potassium? Potassium belongs to the fourth period and first group. So as the period number is 4, it will have 4 shells. Let us look at the group 2 elements, beryllium and magnesium. Beryllium belongs to the second period. So it will have 2 shells. Magnesium belongs to the third period. So it will have 3 shells. Now what about fluorine and chlorine? Fluorine belongs to second period. So it will have 2 shells. What about chlorine? Chlorine belongs to the third period. So it will have 3 shells. So from this we conclude that once again what we learned from this? We learned that down the group, as we move from top to bottom of a group, the valence electrons in a particular group will be always same. The second point, down the group, what we observe that the number of shells are getting added. The number of shells increases down the group. Now let us consider the second period elements. You know, first period elements are hydrogen and helium. Let us consider the second period elements now. The second period elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Their atomic numbers are 3, 4, 5, 6, 7, 8, 9, 10 respectively. Now let us write the electronic configuration of second period elements. The first element is lithium. Its atomic number is 3. So what will be its electronic configuration? 2, 1. Because the first shell can accommodate maximum 2 electrons. So out of 3 electrons, 2 is given to first shell. So remaining 1 electron goes to the second shell. Now let us look at the second element, that is beryllium. What's the atomic number? 4. So what will be its electronic configuration? 2, 2. That's right. Now let us look at the third element, that is boron. What's the atomic number? 5. So what will be the electronic configuration? 2, 3. Yes. Now next element is carbon, atomic number 6. Electronic configuration will be 2, 4. Then nitrogen, atomic number 7. Electronic configuration will be 2, 5. Similarly, the last element of the second period, that is neon. Its atomic number is 10 and its electronic configuration will be 2, 8. Do you see anything in particular about the number of valence electrons in this period? You see, what's the number of valence electron in the first element, that is lithium? That's 1. Now, what is the valence electron in the second element, beryllium? That is 2. Valence electron in boron, 3. It goes on up to what is the valence electron in neon? 8. So, here we observe that in a period, if you move from left to right, what happens to the number of valence electrons? The number of valence electrons increases by 1 unit. Now, one more result you can draw from this representation. That is, you see, what are the number of shells present in all elements of this period? See, the first element of period 2 has 2 shells. Second element also has 2 shells. Third element also has 2 shells. So, all elements in period 2 will have 2 shells. I think it is clear to you. So, in a period, when we move from left to right, number of valence electrons increases by 1 unit, and the number of shells in all the elements in the same period, that will be same. So, if the period is 2, the number of shells will be 2. Now, let us consider the third period. What is the first element of third period? That is sodium. What is the atomic number? 11. So, what will be the electronic configuration? 2, 8, 1. Total gives you 11. The second element, magnesium. What is the atomic number? 12. So, what will be its electronic configuration? 2, 8, 2. That gives you 12. So, when you go on like this, the last element is argon. What is the atomic number of argon? 18. So, what will be its electronic configuration? 2, 8, 8. You see, the number of shells here in all the elements of period 3 will have 3 shells. Now, what about the valence electrons? The number of valence electron changes as we move from left to right in that period. Number of valence electrons increases by 1 unit when we move from left to right in a period. Is it clear? So, we have drawn 2 conclusions. The first conclusion is number of valence electrons increases by 1 unit when we move from first element to the last element in a period. The second conclusion, if the period number is 2, it will have 2 shells. If the period number is 3, it will have 3 shells. That means in a period, the number of shells are equal for all elements. Now, the maximum number of electrons that can be accommodated in a shell can be defined using the formula 2n square, where n is the number of shells. So, in the first shell, that is K shell, the maximum number of electrons that can be accommodated is 2n square, that is 2 into 1 square, that is 2. And in the first shell or in the first period, there will be 2 elements. Now, let us look at what is the maximum number of electrons that can be accommodated in the second shell, that is L shell. That is given by the formula 2n square, that equals 2 into 2 square, that is 8. So, the number of elements in the second period, that will be 8. Similarly, the number of elements in third period, fourth period, sixth period and seventh period will be 8, 18, 18, 32 and 32 respectively. And you will learn about these topics in detail in your higher classes. Now, let us discuss about some trends that is seen in the modern periodic table. The first one is valency. Let us consider the first group elements of the modern periodic table. They are hydrogen, lithium, sodium, potassium, etc. You know, atomic number of hydrogen is 1. So, it will have 1 electron in its first shell. Atomic number of lithium, that is 3. So, its electronic configuration will be 2, 1. Sodium atomic number is 11. Electronic configuration will be 2, 8, 1. Now potassium atomic number is 19. Its electronic configuration will be 2, 8, 8, 1. The last session we have seen the number of valence electron in the first group elements are same, that is 1. So here this 1 is called the valency of all these elements. So we conclude that in a group all the elements will have the same valency. The first group elements will have the valency 1, second group elements will have the valency 2 and so on. So down the group valency remains the same. Now let us see what happens to valency when we move from left to right in a periodic table or in a period. Let us consider the third period of the periodic table. Third period elements are sodium atomic number 11, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Argon has an atomic number 18. Now let us write the electronic configuration of all these elements. Electronic configuration for sodium is 2H1 because its atomic number is 11. So 2 electrons in the first shell, 8 electrons in the second shell and remaining electrons will go to the third shell. So the 1 electron is remaining. So its electronic configuration will be 2, 8, 1. Now the second element is magnesium. Atomic number is 12. So its electronic configuration will be 2, 8, 2. Now you see, if you write the electronic configuration of all these elements, what can you say about the number of electrons in the last shell? You see, for the first element, the number of electrons in the last shell is 1, second element 2, third element 3, fourth element 4, it goes on increasing, and for the last element the number of electrons in the last shell is 8. Now let us find out what is the valency of all these elements. Valency is also defined as combining capacity of an element. You see, for sodium its electronic configuration is 2, 8, 1. All these elements try to achieve the noble gas configuration. So to attain noble gas configuration, sodium, there are two possibilities. Its outer shell has 1 electron. So one possibility is to lose that 1 electron. If sodium element loses that electron, its electronic configuration becomes 2, 8. That will be similar to that of neon. Otherwise, it has to gain 7 electrons. Then its electronic configuration will be 2, 8, 8. That will be similar to argon, which is easy. To lose that 1 electron or to gain more 7 electrons, it will be easy to lose 1 electron. So here valency of sodium is 1. Now let us consider the second element, that is magnesium. What is the electronic configuration of magnesium? 12. Atomic number is 12. Electronic configuration will be 2, 8, 2. What is the number of electrons in the outermost shell? 2. So either it can lose 2 electrons, then it becomes 2, 8, or it has to gain 6 electrons, then also it can become 2, 8, 8, other noble gas configuration. But what do you think which is easy? To lose 2 electrons. So the valency of magnesium, that is second element, is 2. Like this, can you tell me what will be the valency of aluminium? Its electronic configuration is 283. Yes, its valency will be 3. What about the next element, that is silicon? Its electronic configuration is 2, 8, 4. Here either it can lose 4 electrons or it can gain 4 electrons. In either case, its valency will be 4. What about the next element, phosphorus? Its electronic configuration is 2, 8, 5. So there arise again two possibilities. Either it can gain 3 electrons to get the configuration 2, 8, 8, or it can lose 5 electrons. So it will be easy to gain 3 electrons. So here the valency of phosphorus is not 5, its valency is 8 minus 5, that equals 3. 3 is the valency of phosphorus. Why? Because it is easy to gain 3 electrons rather than to lose 5 electrons. Now can you tell me what will be the valency of sulfur? Electronic configuration is 2, 8, 6. Last shell contains 6 electrons. What will be its valency? Its valency is not 6. Its valency is 8 minus 6, that is 2. Why? Because either sulfur can lose 6 electrons to get the electron configuration 2, 8, or it can gain 2 electrons to get the electronic configuration 2, 8, 8. So what do you think which is easy to gain 2 electrons? Its valency will be 8 minus 6, that is 2. Now you can find the valency of chlorine. Its electronic configuration is 2, 8, 7. What do you think about its valency? Yes, you are right. Its valency is 8 minus 7, that is 1. Now what about argon? What is its valency? The last shell contains 8 electrons. So its valency will be 8 minus 8, that is 0 valent. They are noble gas or they are inert gases, they are 0 valent. Its valency is 0. From this discussion, we conclude that down the group valency remains the same and across the period valency increases from 1 to 4, then it decreases to 0. Now let us see what happens to the atomic size of atoms when we move down the group and when we move from left to right in a period. You know, atomic size refers to the radius of an atom. Usually the radius of an atom is the distance between the center of nucleus to the last shell of an atom. That distance is usually denoted by the radius of an atom. Okay. Now the atomic radius of the hydrogen atom is 37 picometer. 1 picometer is 10 raised to minus 12 meter. You see, it is a very small distance. Okay, the radius of hydrogen atom. Now let us see what happens to the size of atoms when we move down the group. You know, let us consider the first group elements. We have already seen that topic. In a 1 second, let us just revise it. The first group elements are hydrogen, lithium, sodium, potassium, etc. You see, what happens to the number of shells as we move down the group? You know, as we move down the group, number of shells are increasing. The first period elements will have 1 shell. The second period elements will have 2 shells. Third period elements will have 3 shells and so on. So what happens as we move down the group? The number of shells increases. So as number of shells increases, what happens to the radius? The radius of atom also increases. We say that the size of atoms increases down the group. Now let us see what happens to the size of atom when we move from left to right in a periodic table. Let us look at the second period of periodic table. The elements in the second period are, you know, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. We know the electronic configuration of these elements. Lithium 2,1, beryllium 2,2, boron 2,3 and etc. up to neon. Neon has an electronic configuration of 2, 8. You see, what are the number of shells for all these elements? All these elements will have 2 shells each. But what varies? The number of electrons in the outermost shell varies. So what can you say about the size of atoms across a period, or when we move from left to right in a period? Do you think it is same as the number of shells are equal? The number of shells are equal, but the atomic radius is not same. Actually, the atomic radius is decreasing as we move from left to right in a periodic table. Why? Because you see, the first element has 1 electron at its outermost shell. The second element, that is beryllium, has 2 electrons. Third element, boron, has 3, and the fourth element, carbon, has for electrons in its outermost orbit. So as we move across the period, the number of electrons in the outermost orbit increases. You know what is the charge of nucleus? The charge of nucleus is positive charge because proton is present there and the other particle is neutron, which is neutral. Now electrons are present in the outermost orbit. In the shells, electrons are revolving in the shells. So what happens is, as the number of electrons increases, the force of attraction between the nucleus and the electrons increases. If there is only one electron, the force of attraction between the nucleus and this electron will be less. But as the number of electrons increases, the force between nucleus and the electrons in the outermost orbit increases. So ultimately what happens? The size gets reduced. So down the group, what we have seen? The size of atom increases because as we move down the group, shells are getting added. But across the period, what happens? The size decreases. Why? Because the effective nuclear charge between the nucleus and the outermost electron increases. So as the charge gets increased, the size gets reduced. I think it is clear. Now let us discuss about the metallic and non-metallic properties of elements in a periodic table. Let's have a look at the periodic table. Where do you see the metals? Metals are seen on the left side of the periodic table. You see sodium, potassium, magnesium, all these are metals. Where do you see non-metals? Non-metals are seen on the right side of the periodic table. So we conclude that from left to right, when we move, metallic character increases or decreases. The metallic character decreases slowly and finally it returns to non-metallic nature. Now, in between metals and non-metals, there is one more category of elements. They are known as semi-metals, or they are also called as metalloids. In the periodic table, you can see they are represented in a using zigzag line. The elements belong to metalloids are boron, silicon, germanium, arsenic, antimony, tellurium and polonium. These are called metalloids. Why? Because they show some properties of metals and some properties of non-metals. That's why they are known as metalloids. Now let us discuss about the tendency to lose electron in a periodic table. Let us take the first group in the modern periodic table. You see, the first element is hydrogen, then comes lithium, sodium, potassium, etc. You see, what happens to the number of shells as we move down the group? We already discussed this topic. As we move down the group, the number of shells increases. As the number of shells are increasing, the force between the nucleus and the outermost shell decreases. Why? Because the distance increases as we move down the group. So, what about the tendency to lose the outermost electron? As the force between the nucleus and the outermost electron is not so strong, the outermost electron can be easily moved, or it can be just take away from that metal or from that element. So we conclude that when we move down the group, the effective nuclear charges decreases and the tendency to lose electron increases as we move down the group. It is very simple. The number of shells increases, distance between nucleus and the electron increases. So the force between nucleus and electrons will be less. So the outermost electrons can be easily taken away from the atom or element. So the tendency to lose electrons increases as we move down the group. Now let us see what happens, the tendency to lose electron when we move from left to right in a period. Let us just take the example of second period. The elements in the second period. How many shells will be there in all the elements in the second period? The period number is 2 So the elements in the second period will have 2 shells. But what happens to the number of valence electrons? Valence electron increases, from 1 to 8 as we move from left to right. Then what happens to the effective nuclear force between nucleus and the outermost orbit? If you consider the second period, there will be 2 shells for all the elements. How do you compare the effective nuclear charge between nucleus and the outermost electron? As we move from left to right, number of electrons are increasing. So the force between the positive nucleus and the negative electrons will be more. So what about the tendency to lose electron? The force increases. So the tendency to lose electrons decreases. But what about down the group? The distance increases because shells are getting added up. So the tendency to lose electron increases. But across the period, tendency to lose the electron decreases. So we say that down the group, as the tendency to lose electrons increases, we say that electrons are electropositive. Or we say that as we move down the group, metallic nature increases because tendency to lose electron increases. But what happens to the metallic character when we move from left to right? Tendency to lose electron decreases. So metallic character decreases. So which character will be increasing? The non-metallic character will be increasing as we move from left to right in a periodic table, and metallic character decreases.